But let's keep rolling. Okay, so we just finished a hopefully successful sidebar on acoustics, and everybody at least has an appreciation for what the solution looks like. Pretend you could see behind the screen. What the speed of sound is and what it depends on, and how those two things determine what mode shapes you're going to get to resonate inside of systems like this. So now let's keep that idea of resonance in our head and start to talk about the thermoacoustic feedback loop. So the basic thermoacoustic feedback loop is a coupling between acoustic oscillations and heat release rate oscillations. And so the energy that's transferred is essentially transferred by a compression expansion work process, or a PDV process, which is something you probably learned in introductory thermodynamics. So let's do a quick thought experiment about how this works. So the first thing that happens, let's just say I have some disturbance, and I get a pulse of heat release rate oscillation. It could be high, low, whatever. I kick the flame, and I get a little bit extra flame. What ends up happening is I end up with an expansion, right? Flames, as heat is released, the density goes down, the volume goes up, you get an expansion. That expansion pushes on the air around it and does expansion compression work. Or if you, I don't know how you'd kick a flame and have it be too cold, but if you had a cooling event, then you'd have a compression and you'd still have the same type of work. Work is a way in which energy is transferred, and so now you have this compression expansion work, and if you do compression expansion work on a part of the acoustic field where you have high pressure oscillations, you can essentially pump energy through compression expansion work into the acoustic field in this way. So now you've pumped energy into the acoustic field now oscillates, so you have fluctuations in both pressure and velocity, and because the flame is sitting in the acoustic field, that creates more heat release rate oscillations, and the whole cycle goes around and around. Questions on this? Yeah?
Does this loop also apply in the low Mach region?
Yes, this typically happens in low Mach numbers, and so the mean flow for the flame does not have to be high at all for this to be the case. The speed of sound is still the speed of sound, right? And so the speed at which the acoustic oscillation is propagating through the system is still Mach 1 by definition, but the mean flow that would be stabilizing your flame, can be whatever. That's fine. And we'll see some examples of some extremely low velocities and some sort of middle-of-the-road velocities as well. Other questions? Cool. All right, so if we're going to look at this mathematically, the way that everybody talks about this is through a parameter called the Rayleigh criterion. So Lord Rayleigh was, some, again, like baron in England doing really good science in his backyard. I am a little bit jealous of how science used to be done. He published this treatise called The Theory of Sound, Part 1 and 2, in 1863. And one of the things he talked about, he did not know that this was going to be a problem in rockets, but one of the things that he talked about was this potential coupling between heat and sound. And so he basically says that it's possible, right? He derived this, and so you'll find the name Rayleigh shows up in a lot of thermoacoustics as a result. And so the Rayleigh index is this equation right here. I killed it. Shouldn't have left it on. So the Rayleigh index. Here we go. Get my pointer options. Here we go. You have your pressure fluctuation and your heat release rate fluctuation. If you integrate this over time and you integrate it over an acoustic period T, and you integrate it over the volume of the flame, V, you can basically see where, if P prime is high and Q prime is high, you'd get a high Rayleigh index, so you get a high potential for thermoacoustic feedback. If they're out of phase, and we'll talk about phase in just a second, then the Rayleigh index is negative and you don't have any thermoacoustic feedback. So one quick note, then I'll have a fun sidebar. In reality, there's damping. We're going to talk a bunch about damping tomorrow. And so realistically, you don't just need the Rayleigh index to be greater than 0, you need it to be greater than the damping in the system. Because this is the thermoacoustic driving, and you need your driving to be higher than your damping in order for the system to be unstable. One quick fun thing about the Rayleigh index, or this feedback loop, this doesn't all have to go in the forward direction. And actually, one of the major branches of thermoacoustic research is in thermoacoustic refrigeration. You can use sound to cool down fluids without a refrigerant, which is pretty cool. The refrigerators on the space station use thermoacoustic refrigeration because refrigerants typically aren't great for you, and they don't want to put them in a tiny capsule with a bunch of astronauts in space. The other place that uses thermoacoustic refrigeration is Ben & Jerry's, the ice cream manufacturer in Vermont. At Penn State, we have this thing called the Applied Research Laboratory, which is the Navy laboratory that we operate on campus. And there used to be a really big thermoacoustic refrigeration group, and they did a project once to help Ben & Jerry's pilot a thermoacoustic refrigerator for their ice cream, because refrigerants, or old refrigerants, are pretty serious greenhouse gases, and so this was a way to lower their global warming potential. So fun ice cream connection for thermoacoustics there. But here we're going in the opposite direction. It's not something we want, same types of principles apply. Okay, so very briefly, I had mentioned this idea of phase. And so we're going to quickly step through the math with some pictures to understand what's going on. So what I've done here is I've just plotted some sine waves. So let's pretend that both P prime and Q prime are only oscillating sinusoidally, which isn't realistic. Usually Q prime has a bunch of turbulent terms, right? Because flames are often turbulent. But the black line here is P prime, right? And so we have this nice sine wave. And you can imagine that if you have different phases between the oscillation and the pressure and the heat release, you get different values here. So a good example, this blue dashed line is pi over 6 phase difference. So the black is the pressure, this is the heat release rate. And if I multiplied these two, there are only a few places where this is negative and this is positive. For most of the signal, both of them are either positive or both of them are either negative, and so the Rayleigh index ends up being positive. You can see that switches, so pi over 4 is the dashed line here, and then you get pi over 2, which is 180. Obviously here they're always out of phase, because that's what pi over 2 means, but pi over 4 or 90 degrees is kind of the cutoff. Right? Here you have half the signal that's positive and half the signal that's negative. And so your Rayleigh index, again, if these were just pure sines, would be 0. If you have anything less than 90, you end up with some positive component. Anything greater than 90, you have a majority negative component. And so you end up with a Rayleigh index that's less than 0. So what this tells you then is the name of the game thermoacoustically is the phase. So if I took this figure from a tutorial I teach with Tim Lewin at Turbo Expo. But basically what this shows is, you could ignore what this is. We'll talk about this in just a second. Assume that the x-axis is the phase, but not wrapped, right? So, if you wrap a phase, you go from 0 to 2 pi, and then you start again 0 to 2 pi. Let's just keep counting, right? 360, and then 720, and then just keep going, right? And so there are these regions where you're between negative 90 and 90 degree phase, where you end up with a positive Rayleigh index, and so you end up with a positive driving for the system, and so you can have a thermoacoustic instability. But then you have these other regions where the Rayleigh index is negative, and they're at least greater than 90 degrees out of phase, so you don't have any driving, and you have no thermoacoustic feedback. But because things happening harmonically are just on a big circle, if you keep going, you're just going to get to another region where these line up again, and then another dead region, and then another region where they all line up again. You can, questions about this before I start showing some data? This is just like a fun fact of harmonic signals, but it has some really massive implications for instabilities in actual systems. So, you know, this figure and that figure were made in MATLAB. This is data that was measured at, where was Jeff when he did this work? I want to say it was UTRC, potentially. But this is data that was measured on an actual combustor. So what's happening in this picture is over here you have the flame, and you have some fuel injection point, which basically tells you we'll see why this matters, but it basically determines the phase between the heat release rate fluctuation and the acoustics. The acoustics don't change as you change the location of fuel injection. Changing the location of the fuel injection just changes the phase of the heat release rate. And so you can see as they move it back, you get regions of positive and then nothing, and then positive and then nothing, right? And this is all continuous. They're not moving it back and forth, they're just moving the fuel injection back continuously. But because these oscillations are heading in a big circle, or you know, sine waves repeat in a big circle, you get this phenomenon. This is another example. So this was work done by Tim when he was a grad student of benzenes at Georgia Tech. And now you have, instead of changing the phase, what they did was they changed the velocity, and you can see different frequencies show up, right? And so so at the beginning, here you can see this frequency lines up and then goes away, but then this frequency pops up later and then goes away. And so we see this periodic appearance and disappearance, and as we go through, we'll talk more about why inlet velocity matters and why the different frequencies are popping up. But I just wanted to show some actual data where you see exactly that shape that you'd predict by multiplying sine waves in the Rayleigh integral in actual data from turbulent flames. So, key point. Because instability is non-monotonic, so this behavior is called non-monotonicity, you're changing something in one direction, you're changing the phase, or the fuel injection location, or the velocity, or whatever, and the response of the system does not always go in the same direction. Changes to any operating parameter will never suppress the instability. It always depends. So I cannot tell you the number of times where people have asked me, like, well, if we increase the amount of hydrogen in a system, will it make instability better or worse? I don't know, man. Like, this, right? It could make it better or it could make it worse. And then it really depends on what your operating condition is. You can say the same thing about temperature, flow velocity, you know, anything. As long as you're changing one of these two things monotonically, and usually what you're changing is the phase of Q prime, because the acoustic field kind of is what it is, then, you know, you have these regions, these islands, remember I told you about these islands of operation where it's going to be unstable, and then these islands where it's stable. Does this make sense? Questions? Okay, so this is what makes it fun, right? This is job security, friends, because it means that everything is hardware dependent. Okay, so let's look at a good example. So this is the one we use when we teach this tutorial. If anyone's at Turbo Expo this year, you can come see the Tim and Jackie show and see this slide again. This is an example where we go from condition 1 to condition 2. Here the flame gets shorter, so this could be like adding hydrogen to natural gas. And if condition 1 is stable, by moving the flame up, you've moved the phase of the heat release rate oscillation closer to the phase of the pressure oscillation. You've moved it past that 90-degree mark, and now it's unstable. And that just had to do with where stable was at the beginning. But you could play this game again. There we go. Where, let's say, the longer flame was unstable, and the shorter flame, as you move that phase back, actually makes it stable. And so the answer to every instability prediction question is, it depends. So at Penn State, I inherited a couple really cool combustors. They were built by Don Santovica's group before he retired, and I was very lucky to get them. And so in this combustor, we can do a lot of cool things. This is the cross-section of what it looks like. You can see we have an injector here and a quartz liner, so we can see the flame. You can see injector, quartz liner. But the really nifty thing about this combustor is we can change its length while it's operating. And so inside this long tube at the end, there's a water-cooled piston, and there's a stepper motor here on a translation screw. And so you can move the piston back inside and change the length of the combustor as you're going. And so one of the things we always do, because you're changing the length, you're sweeping through, in this combustor, 4 different acoustic modes. And so you can really work out the flame in a lot of different ways by changing the acoustics of the system. And so Don's group took this really nice map of one of their injectors. On the x-axis, they're changing the combustor length from like 25 inches to 53 inches, or I guess this was only 51 inches.
The y-axis.
Huh?
You're changing it on the y.
Yeah, sorry, on the y-axis. And then on the x-axis, you're changing the adiabatic flame temperature, which, let's just say, they changed it using equivalence ratio. This data was taken a really long time ago, before I started in the group. And in the colors are the instability amplitude. And so you could absolutely see, the way we'd operate this is we'd start at 25 inches and we very slowly move the piston back, and at every inch or so, we take a pressure measurement. And you can see just this big island of instability at different, and if you looked at the frequencies, these blobs, like this blob and this blob and this blob, would all have different frequencies. Because the length of the combustor is different. But at each length, you don't always get an instability. So for example, at 35 inches, colder flames are perfectly quiet. Hotter flames are very loud. And so this all has to do with that phasing between the pressure and the heat release rate. Okay, questions on that? So phase matters, everything, phase is everything. All right, so phase is everything, so that tells you if you're going to get driving or not. But then the second question you have to ask yourself is, well, what's the amplitude going to be? Because if it's a really low amplitude, like maybe I don't care, I mean I care, but maybe my engine doesn't care. But if it's a really big amplitude, then my engine's definitely going to care. And so this is sort of the holy grail of instability work, is to predict this final amplitude. It's not easy to do. And this chart explains why. So what I'm showing here as a function of oscillation amplitude A is what the typical damping of a combustor looks like. Damping's kind of linear, most damping. And so we're going to approximate it as linear. The other thing I'll say, measuring damping is really hard. There are only a couple people that do it well, and under very controlled circumstances. And so every once in a while when I think like, man, I'd like to attack a really difficult problem, the first thing that comes to mind is I'd really like to measure damping better. Then I think, no, it's going to take all my time. So maybe it's not going to happen. But it's really difficult to measure. We do know, however, that from acoustic theory, it's typically linear-ish. And so what really matters, going back to our really criterion here, is the thermoacoustic driving, is the phase relationship between these two things such that my thermoacoustic driving is greater than the damping in my system. And so in a stable system, the answer is always no. And so what I'm showing here is the thermoacoustic driving, which for some reason we call H in plots like this. And you can see that as a function of amplitude, the thermoacoustic driving never gets greater than the damping. And so if I always have a competition between these two things, I will never see a tone because it'll be damped out. One thing you'll notice, and we'll get to this a little bit more in a second, is that this is not a line. Flame dynamics, as we'll see soon, are typically not linear. It looks linear at the beginning, right, at small disturbances, and then it becomes nonlinear. So this is a stable system, but if I want to figure out what the amplitude of my unstable system is, I have to have a situation that looks like this. And this is a pretty typical driving curve for a flame. You have a region where the response of the flame is linear, and so that means that when I put in some perturbation of amplitude A, I get out some response HA, and if I keep increasing the amplitude A, that response increases linearly. So going back, this is another application of the idea of linearity. But at some point, and we will see why by the end of today, flames stop acting linearly and they start saturating. And so you get a point in this saturation where now your driving equals your damping, and this point is called a limit cycle. And it is this amplitude at which the system will sit, and this will be the amplitude of your instability. The reason is that this is a point, from a dynamical systems perspective, this point is stable. There are two, there's an unstable fixed point and a stable fixed point. We're going to change things up a little bit. I could sit at 0, 0, right? This is where those two are also equal. But if I put an infinitesimally small perturbation to this system and poink, send it up a little bit, now my driving is higher than my damping and the system amplitude will grow. But now if I sit at this other fixed point and I poink, hit it to the right, now the damping's higher than the driving and it's going to drive the system back to the left. And if I hit it poink to the left, now the driving's greater than the damping and it's going to push it back to the right. So this is called a stable point for the system because it'll just sit here. If I poke at it from this point, it'll go back to that amplitude. But we call this now an unstable combustor because it's screaming, because typically limit cycle amplitudes are pretty high. Show of hands who's taken a nonlinear dynamics course? Couple people. So this is like nonlinear dynamics 101, right? So fixed point, limit cycles, all that kind of stuff. This is one of the reasons I really like thermoacoustics as a discipline, because you get to learn so many things, and nonlinear dynamics is one of them. Okay, you can imagine though that predicting nonlinearity in any system is really difficult. Anybody out there who's doing simulations, or particularly anybody who's doing theory, will know this. Measuring nonlinearity is no cakewalk either. And so this is why predicting the amplitude of instability is quite difficult. We're really good now at predicting the frequency because calculating acoustics is pretty easy. This is a really easy equation to work with here. That one. And we can get pretty good at determining the phase between the heat release rate and the pressure, but figuring out the nonlinearity of the flame response is quite difficult. And we'll see why in just a bit. All right, any questions on this before we keep going? Yeah.
So, like, if I get it correct, so you are telling that if the instability, like, if you're increasing in instability, at some point it's going to be stable or it's going to be like non-damping? Get it?
Yeah. Okay, so there's a difference between the flame being unstable and the system having a stable solution, right? So this is a stable solution to the equations, because if I perturb the system around there, it'll always go back. But we call this is the point of combustion instability. I mean, it's unstable all the way up here, right? Because, you know, driving is always higher than damping. But this is the point where it's going to sit. And so the point here is that it won't grow indefinitely. That would be exciting, but doesn't happen because nonlinearity kicks in, and so you get to an amplitude, or your limit cycle amplitude, where it tops out. But that's a stable solution of the system. Yeah?
It seems to me that this theoretical solution, it exists, but in experiment we may not even reach this point before our system explodes.
Nope, you always reach this point. I mean, I guess the system could explode before you get there, but I showed you this data. All of these are limit cycle amplitudes. It gets, well, I think I have some data in here. I do have some data in here that shows the growth rate. I'll show it tomorrow. But it grows very quickly, and then it just gets there. And this is the amplitude that it sits at. So every single instability point, and you can see the percent, so this is the RMS of the pressure fluctuation over the mean, which for this rig is atmospheric. So it's anywhere between, I don't know, 1% and really bad day 4% of atmospheric. That's not going to blow the system up. It's loud for sure, but these are all limit cycle amplitudes. Yep, it's a good clarification. Yeah.
What was the vertical axis on the plot between the driving and the damping?
Oh, it's just the amplitude of driving versus damping.
It's amplitude on both axes?
This is the amplitude of the disturbance.
Okay.
This is the amplitude of the response. Yep. Other questions? Awesome. All right. So I told you all those things, and all those things are true, but it's not the whole picture. Because in real systems, you very infrequently just have a pressure wave that drives heat release rate oscillations. And so what you typically have instead is something called a coupling mechanism as the mediator in between. So you have your same acoustic oscillation. That acoustic oscillation triggers something. I shouldn't use the word triggers. It causes another oscillation, and then that other oscillation drives the heat release rate oscillation, and then you get the compression expansion work that feeds back into the acoustic oscillation. This is where the fun is from a research perspective, because there are a number of different coupling mechanisms, and they all rely on a lot of different physics. And so I'm going to introduce a few of them briefly, and then tomorrow we'll see more examples of one in particular, because it's the one I study. And we'll look at that in a little bit more depth. So actually, pretty early on, we knew that this was a problem. So this is a really famous paper by Rogers and Marble from 1956. And what they're showing, this was a really cool experiment. It's just a bluff body stabilized flame. So you've got this like triangular V gutter kind of flame holder thing. And the flow's going by. This is a spark-Schlieren photograph. And you can see where the flame is. They call it smooth combustion. It's not wording we use anymore, but it's kind of fun. And you can see, your flame sitting in your shear layer and everything's going like it's supposed to. And then they would change the fuel-air ratio. And at some points, you would get very unstable combustion. They called it screeching combustion. We do still use this nomenclature. We have great nomenclature for instabilities, like screech and rumble. It's a lot of good words. Anyway, so they called this screeching combustion, and you can see that there are these large-scale structures in the flame. I will be the first to say that one should not infer a velocity field from a Schlieren photograph, but we're going to infer a velocity field from a Schlieren photograph because you can really clearly see that this is vortex roll-up on the shear layers that are separating off the bluff bodies, right? The other thing to notice is that this is anti-symmetric. So if you like drew a line, here's the first little vortex. It doesn't have a partner up here. This one is in the braid of this one. And so the reason this is called screeching is this is not a longitudinal mode of this system. This is a transverse mode of this system. And when you get those really high frequency transverse modes, it is loud and very high frequency. Again, the frequency is high, going back to the equation here, because if the frequency is high, the wavelength is short. Or if the channel you're trying to fit this in is short, then your frequency is going to be high. And it comes out screeching. So this will be on the order of 1,000 to 2,000 hertz, which is very unpleasant. Anyway, so Rogers and Marble in 1956 knew that this was going to be a problem just from these images. There are, however, different types of acoustic velocity fluctuations that you see. And so the first coupling mechanism that we're going to look at is called velocity coupling. And so this is where the fluctuation in this coupling mechanism bubble is a velocity fluctuation. And so you have some acoustic fluctuation that drives a velocity fluctuation, and then it's the velocity fluctuation that drives the heat release rate fluctuation, and then you close the loop with compression expansion work. There are two different types of velocity fluctuations that are interesting in combustion systems. One is acoustic, and we're going to see this video later. It's a very famous video that Daniel Girac took at what was then École Centrale. You can see really beautifully, again, a Schlieren video of the flame front. Very, very low very, very low velocities. It's just a laminar Bunsen flame. And so they have a speaker on the bottom. They're forcing it. I think this was at 50 hertz or something. And you can really nicely see the oscillations in the flame that come from that. We're going to explain this by the end of today with the help of some pipe cleaners. But these come from acoustic velocity fluctuations. You also have vortical velocity fluctuations that occur because of the separation of flow off of shear layers. And so this is some data from an academic sibling of mine, Santosh Shambhog. He had a triangular bluff body, just like Rogers and Marble did in a much smaller experiment than theirs. And you can see the plots here of vorticity. He's got a speaker down here, and he's forcing it, and you can see that the acoustic fluctuations drive vortical fluctuations, and the flame, which is this black line, wraps up really nicely around that vorticity. How are we doing on time? Let me look at something super quick. I think we'll be okay. All right. I want to do a sidebar, but, you know, going to the board is a bit of a pain. But we're going to do it anyway because I think it's important. Okay. Before we go on, I want to quickly talk about disturbances. Because my life changed when I read this paper, and I hope yours does too. So the paper I'm referencing, which you can't see but I'm holding, is by Chu and Kavazne. The reference is in the slides. It's called Nonlinear Interactions in a Viscous Heat Conducting Compressible Gas. A real banger, let me tell you. But basically what they go through and do is they decompose fluctuations in a really unique way that I think really helps you understand a lot of thermoacoustics, which is why I wanted to go through and do it. So when we talk about decompositions, right, we typically think about something like the Reynolds decomposition, right? So the Reynolds decomposition says that some velocity of x and t can be decomposed into its mean plus its fluctuating, right? And if you're gonna go through the heartache of deriving the TKE equation, this is the first thing you're gonna do. If you work in unstable fluid mechanics, which we'll see, you will often do a triple decomposition, right? So that says, okay, same deal here, but now I have maybe a coherent part plus my random part. And then there are entire papers written about how you define your coherent part. My favorite is a paper by Hussein that's just called Coherent Structures, Reality or Myth? Question mark. It's really good. But the one we're going to use, and again, getting back to this theme of linearity, is an order-based decomposition, which basically says, I can take, now if I'm going to look at some fluctuation, so I'm going to go straight for the fluctuation, I can don't go straight for the fluctuation. I have some velocity field, and I can decompose it into orders of things. So I have 0th order, which is basically the same as my mean. And then I have orders of fluctuation. So I have my first order, my second order, my third order, whatever. My first order or my linear term is, the biggest contribution. Second order contributions less, third order contributions even less. If you've ever done an asymptotic analysis, this is essentially what you're doing, right? And so what this paper looks at is, okay, I've got my mean flow, great. But I'm going to look at leading order oscillations or linear type interactions in compressible flows with heat release. And I just want to start to describe what types of different interactions there are. And there's a lot of discussion about the arbitrariness of what they do next, right? But the way they decompose it aligns with the mathematics that we use in our conservation equations, right? We're conserving momentum, energy, mass. And it's actually quite brilliant. So basically what they say is that there are 3 different types of disturbances. There are acoustic disturbances, there are vortical disturbances, and there are entropy disturbances, or I'm going to call them entropic disturbances. And these are completely separable. And so if I think about velocity coupling, it's actually quite useful to break it down this way, because now if I think about the different types of disturbances, I can actually pull them out of my data or my analysis quite easily. So assuming I'm in free space, right, so I'm not near any boundary conditions, this all breaks down if I'm near any boundary conditions, but if I'm in any free space, I can look at my vortical disturbances, and I can say that the cross product, or the curl of U vortical, so they called vortical, so they use the subscript A. Is it A? No, he uses the subscript P. Subscript omega and subscript S. But the curl of my vortical velocity disturbances is just my vorticity. That makes sense? That's how we define vorticity. But the divergence of my vortical disturbances is 0. So this says that all vortical disturbances are rotational but non-dilatational. Interestingly, also, they propagate isentropically. So the entropic component of vorticity is 0. Usefully, acoustic disturbances, the curl of an acoustic disturbance is 0, and the dilatation is, they give it some value, Q sub P, which is super confusing because we've been using Q for heat release rate. So this is not heat release rate, this is another value. And similarly, P sub S is 0, or pressure disturbances propagate isentropically. But this is really nice, right? Because you're sort of in opposition here. And so if I have a velocity field and I take its curl, I get all the vortical components. That if I have a velocity field and if I take an isothermal velocity field and I take its divergence, I get all the acoustic components. The thing that really starts to screw stuff up in reacting flows is the entropic component here, which is non-rotational, so that's good for vorticity, but it is dilatational, right? If I add heat to something, it expands. That was kind of important for the thermoacoustic piece. But this is one way, again, I would highly recommend you read the paper, but we're going to talk about vortical fluctuations versus acoustic fluctuations, and I just wanted to get this math down on here because there is a rigorous way to define this. And I tried to do this once in my PhD, actually take data and do this decomposition on the data. Taking curls of data is quite nice. Taking divergence, whew, that got gross. That didn't work out super well. If you have long wavelength oscillations, it doesn't, the noise just takes over. But the other thing that was happening, at least in my case, was you had a flame in there, which was also causing dilatation. So just a quick heads up, this decomposition is out there. People who do this type of work tend to rely on it a lot because it really, really nicely explains some stuff about disturbances in general. While we're waiting for this to very slowly come back down, any questions? Has anybody seen this before or read Chewing Kvasny? No? Okay. Like I said, it's 20 pages of a whole lot of math, but it did really change my view on just disturbances in general, which is a lot of the work that my group does. Okay, so now that we know that these two things are different, are real and different and rigorously separable, let's keep hauling on, sidebar over. Let's keep hauling on coupling mechanisms. So it turns out that once you know what the disturbance mechanism is, or the coupling mechanism is, you can then think about how it affects the flame. This flow chart was put together by my academic brother, Sri Krishna, who, and I just took it straight from his thesis because I don't know if he put it in a paper ever, but I was extraordinarily lucky to go to grad school with this guy because I learned a ton from him. The theory that he did was really fantastic and very helpful. So basically what this outlines is the different ways in which different perturbations can lead to heat release rate response. And so if you have some velocity perturbation, the first thing it can do is change the area of the flame, and that can cause heat release rate oscillations. If you have more flame area, you're pushing more reactants through and converting them to products and releasing heat as a result. The other thing you can do is you can change the flame speed. So this is basically for a premix flame, the statement of heat release at a given time. It's an integral over the area of the flame of the density times the flame speed times the heat of reaction. Right? And so with a velocity fluctuation in a perfectly premixed system, you're not changing the density or the heat of reaction, but you could be changing the flame speed through stretch effects. And he did some really nice work. He and one of the senior students in the group at the time, Princeton, did some really nice work to look at when stretch effects actually matter. And the answer is at really high frequencies. So these are the two mechanisms at work, and we'll see why this is by the end of today. The next coupling mechanism that you often see is equivalence ratio coupling. So basically you can imagine, this is a pretty typical premixer system for industrial or gas-driven applications. You have some air coming in, and you have fuel being injected, but you don't choke your fuel injection, right? If you choke your fuel injection, A, it's really hard to change the operating point because it's only choked at one point. And B, then you really got to back pressure the system, and pressure is money, right, in a pumping system. So you don't choke the fuel injection system. So if you look at what's happening, if you have an acoustic fluctuation in your system, you can imagine if I look at one of these little fuel injection holes, the pressure of the air above the hole is fluctuating, right? Because I have the mean pressure and then some acoustic fluctuation. If I have the fuel pressure, which is always greater than the air pressure, or else the fuel wouldn't leave, I can turn that into a fuel mass flow rate, which if the air pressure is fluctuating is going to end up fluctuating, right? And that's problematic. So if I have an acoustic fluctuation and a non-choked or non-perfectly premixed mixture, I can end up with fluctuations in the fuel-air ratio or the equivalence ratio that then lead to heat release rate oscillations. The diagram here is much more complicated because now the mixture composition affects all this stuff. And so you have heat of reaction perturbations, flame speed perturbations, which can cause flame area perturbations. All of this feeds into different pathways to the heat release rate. His big contribution for his thesis was doing a lot of really good work on this. And it's very instructive. I'm not going to go into the details, but definitely worth reading if you're interested in this work at some point. Okay, so in a real system, you're going to have some combination of all these things, right? You might have multiple velocity disturbances, right? You certainly have an acoustic velocity disturbance. Because you have an acoustic mode in there. You may have a vortical velocity disturbance because you've put your flame in a shear layer, so you have a separated shear layer that's susceptible to disturbances. And you didn't choke your fuel system, so now you have an additional source of coupling through the heat release or through the equivalence ratio. And these all start to pile on top of each other. And so the ultimate phase relationship between the pressure and the heat release rate is much more complicated. So this is from a really, really excellent review paper by Sébastien Ducrix and some of his colleagues. If you're interested in this at all, this is like Coupling Mechanisms 101. It's really beautifully written. And here they give an example of all the different coupling mechanisms and the heat release rate and all the different things that have to add up from a phase perspective to help you determine whether or not you're going to get a instability or not. So, key point, keep track of your phase lags, because that's what's really going to determine whether you have an instability or not. Okay, so we're going to keep going because we have break in 10 minutes, but this is actually going to work out well because I'll be able to introduce this, and then when you come back from break, you can grab your crafts, and we'll do our flame kinematics with crafts. Okay, so I've been talking about flame response. Now I'm going to play this really nice video. So this is what it looks like, right? So this is a laminar Bunsen flame being forced at 50 hertz. And you can see from this Schlieren movie that you get really nice wrinkles on the flame. And if you just, kind of imagine what's going on, the flame area is changing, which means that your heat release rate is changing. And that's the coupling between the acoustic fluctuation. So here you have an acoustic velocity fluctuation that's changing the flame area that then changes the heat release rate. One of the things I find lacking in most people's understanding is the reason that the flame does this. And that's what we're going to focus on for the rest of today. This is a process called flame kinematics. Why, when you hit a flame with the sound wave, does it dance like this? What determines the angles, if you look at the base of the flame, what determines the angles that are being formed and the fluctuation level of those angles? You can see as the disturbance forms initially, it's nice and rounded, right? And then it turns into this cuspy thing and then annihilates itself at the top. Somebody said they were working on flame annihilation before. This is a really great example of flame annihilation. All these dynamics can be explained pretty simply with flame kinematics. And understanding this from a fundamental level is quite important, I think, to understanding bigger, even like highly turbulent systems. You can still get a good grip on what's happening by understanding what's happening with laminar flames. So, just a quick reminder, I'm assuming we all get this, but premix flame propagation, if I have a flame inside a tube and some fuel and air coming at it, if I want the flame to be stationary in the reference frame of the laboratory, then I have to set this incoming air velocity to be equal to the unstretched laminar flame speed if this is a one-dimensional situation. I will also remind us that unstretched laminar flame speeds are not fast, right? So this is from Glassman, Yetter, and Glumac. This is just a bunch of flame speeds for different fuels as a function of equivalence ratio. We're talking centimeters per second. These are not fast-moving things. A key word here is kinematic condition. So the kinematic condition is met when the flame speed, which is the speed at which the flame propagates normal to itself, is equal to the velocity component normal to the flame. Here in one dimension, it's just U is equal to SL. But that normal component, as we'll see when we come back from the break, is quite important. Right? Flames propagate normal to themselves, and so what matters for how they stabilize is the velocity component that's normal to the surface of the flame. And so we can see this in two dimensions by looking at just a flame stabilized on a rod. Here the flame is stabilized at some angle alpha. And if the kinematic condition was met in one dimension, if SL was really equal to U, then the flame would be sitting horizontally, right? Because along the length of the flame, it would all be equal to the incoming flow velocity. But if combustors had to do that, they'd be very slow, right? So we don't rely on that. Instead, we up the velocity, but when we do that, the normal component to the flame needs to go down because, or needs to stay the same because the flame speed's staying the same. And so what happens is the flame tilts, right? And so now the normal component, or SL, is equal to this incoming component times the sine of the flame angle. And that, if you know what your incoming flow velocity is, and you know what your flame speed is, then you can calculate your flame angle, again, assuming laminar, no stretch effects, all that jazz. Questions on this? Has everybody seen this in a combustion class? Maybe? Some heads nodding? All right. So then as you increase the velocity, this is my terrible PowerPoint art. As you increase the velocity, you're going to go from a very wide flame to a very tall flame to eventually a flame where you can't stabilize anymore because you can't burn a flame that's completely perpendicular to the direction of the flow. You need to have some normal component. And so we're going to take our break a little bit early. While I was making this presentation, I was using the slide designer way too liberally. And when I put in the title, Now with Crafts, this is the picture that it put up. And I sat in my office like laughing for several minutes. And I was like, this is a very prestigious summer school. And they're going to get this picture. And so when we come back, I'm going to give everybody, I have our crafts. We're going to get compostable straws and pipe cleaners for you to keep, my present to you. And we're going to play around with the kinematic condition, starting with steady flow and then unsteady flow. But before we do this, I think we deserve some caffeine. So let's take a break. And then maybe let's come back at 4:25 instead of 4:30. Is that cool? All right, thanks team. Now I'm gonna leave this up just in case Professor Law comes in.